In this video, I thought I'd use Excel to look at the fractional part of a fixed point number in binary. So I have so many bits to represent the sort of fractional part. And in this case, I'm going to take 8 places, and I want to sort of show if you have a a fraction in decimal and you want to convert it to binary, sort of like an abbreviated way to do it if you know the number of bits. So again, if you knew it was going to be 8 bits that you wanted. So I'm starting off here in Excel. I have just numbers. This is the 0 and then negative numbers going down, and these are going to be my powers of 2. So in a binary number, fixed point number, the number after the first number after the dot is the halves place, then the quarters place, then the eighths place, and so on. So I have here is sort of the power, -1, -2, -3. Here is 2 raised to that power, a half, a quarter, an eighth, a 16th, and so on. And then I just sort of made up some particular problem and had some coefficients here, 0, 1, 0, 1, 1, 1, 1, 0. And then down here in this last row, I did a product of the coefficient and the power, the negative power of 2, and then finally over here, sort of added them all up. So I had, and to start off with, I had 0 halves and 1 quarter and no eighths and 1/16th and 1/32nd and 1/64th and 1/28. And that all added up to 0.367. There's just some example number. Okay. And then if you had this number, and you wanted to generate the representation for it, a sort of iterative approach would be to multiply that by 2, and that corresponds to shifting your binary. And that makes sense because if I can think of if I were to take this 1 times a quarter, which is one part of my number, and if I were to multiply that by 2, I can think of multiplying the 1 quarter by 2 and making it 1/2. And so then I would have, if I multiplied this number by 2, this number by 2, I can think of multiplying all these powers by 2, which would raise them 1 power, but I can just achieve that by shifting my number. So I took my 0, 1, 0, 1, 1, 1, 1 and made it 1, 0, 1, 1, 1, and then I stopped another 0 on the end. And so I just sort of copied my formulas down. I shifted my number over by 1. And so shifting a binary fraction, any binary number, strictly speaking, but shifting this number by to the one by 1 place to the left is sort of equivalent to multiplying by 2. So we see it here, 0.367, 0.734. This is the one above, multiplied by 2. So shifting is multiplying. So I multiplied by 2. I'm going back. There is this iterative method for getting the binary fraction. And then I kept one place, I kept the ones place, I kept the 0 power. And when that shifted in, that blue came over and became the, I probably should have put it up here in the coefficients and not in the bottom line, but that 0 comes over here into the ones place, and this is how you build up the number as you get what's in the ones place. That is what you're going to keep and represent. So the when representing this number, the first number we're getting is 0. So we multiply our number by 2 and ask sort of, is it greater than 1 or not? It was not greater than um, not greater than 1, so our coefficient was 0. Shift again, so multiply by 2 again. So here's my pattern: 1 0 1 1 1 1. Multiply the whole number by 2. Same game, that it shifts it to the left, and now in my ones place I have a 1, and that got me again point and multiplied this number by 2. So each time I shift, I'm multiplying the thing by 2, and I am picking up in this ones place, I am picking up the bit I want. So one by one in this iterative process, I'm picking up the bits that I want. And what I did here, when I had a number that was greater than 1, I threw away that 1. And so as I proceeded, I multiplied just the fractional part, 0.468. And so that's how I can sort of do it iteratively and get one bit at a time. So I have some number. I can think of it in so I picked a number that can be represented exactly in binary, but I had some number, and then I multiplied, and here was its binary representation, and I had the number. And then I saw what happens if I multiply that number by 2, and I showed that that sort of ends up to be the same as shifting the binary coefficient numbers, and that gave us a representation. So in one sense, I had put in this number, but I'm also sort of getting it out bit by this process of multiplying by 2. So here was my first multiply by 2. Here's my second multiply by 2, and that gave me a 1. My third multiply by 2 gave me a 0. My fourth gave me a 1. And so I'm reproducing the original number 0, 1, 0, 1. Okay. So that is standard iterative process, repeated multiplying by 2 to pick out the sort of binary representation of a fraction. I did it again, but instead of stopping at the ones place, I just carried on with more places instead of having just having the on the positive side or on the left of the dot separating the sort of whole number from the fraction. Instead of just having the ones place, which I had on my previous sheet, I decided to keep 8 more places. So I had 8 in the fraction, so I kept 8 over here. But I was only dealing with the fraction, so they were 0. But what I'm going to stop doing is when I went from the 1.4 over here, I sort of threw away, I ignored this 1. I'm going to stop doing that and just play this new game of shift, multiply by 2, shift, multiply by 2, shift, and then do that 8 times. And then the number shifts all the way over here. So I multiply by 2 and multiply by 2 and multiply by 2. Every time I multiply by 2, I shift. I had a binary fraction that was using a byte, 8 bits, and so I shifted it 8 times, and that got my coefficients all over into the positive range. And so now I have just after I did that, I end up with a 94. So I had some number repeat, and ended up with 94. And then, so we can see that here, I sort of got my original number and I multiplied it by 2 to the 8th. And there's my 94, which I also got through my process of shifting. And I can say, Excel has this dec2bin function so I can get the binary representation of my decimal 94. And I can see it's my original pattern. It's not displaying for me the leading zero, but it's showing me 10111110. Okay. So you don't want to do all this anytime you want to convert and get a binary fraction, but let's take the lesson of we can multiply by 2 repeatedly, and we can eliminate this sort of throwing away the 1 and just sort of keep it and keep shifting. And then what we get is a number. Then if we know its binary representation, it's equivalent to the binary representation of the original fraction that we want. And so all we have to know is the number of places we want to represent. So let's do it for our particular number and then do it for a more general number. So we had a fraction here. Let's see if I can copy that number over into the calculator. Control V, it did, it worked, okay. And then I'm going to multiply that by 2 raised to the 8. And there's my 94. This one's exact. So I'm going to take that 94 so I can copy that, and then switch view over to programmer view and paste that, Control V. And there is my pattern, 0, 1, 0, 1, 1, 1, 1, 0. Okay, so so that's just turning this process around and sort of, instead of one by one getting the bits, getting all the bits we want in one fell swoop. So let's take some number. Let's go back over to scientific mode. Let's say I have 0.707 or something like that, close to the square root of 2 or something. And I want 8 bits. So I could multiply that by 2 raised to the 8. So instead of doing this 8 times to get to get my little bits one at a time, I can just put them all together, multiply by 2 to the 8, get my result. Now here's an interesting point because I have 180.992. And this is, people will take a different approach. Some people will round and do 181, and some people will truncate and just do the 180. Myself, I'm more of a truncator, so I'll take the 180 and take it over to the programmer mode, paste that in, and then down here is my representation. It starts with a 1, and that makes sense because that first place is the halves place, and my number was 0.707, and so I expect a 1 in the halves place for that number. If I have a very small number, let me go back to scientific, 0.123, then multiply that by 2 raised to the 8. Let's say again, I want 8 bits, 31. I'm going to take my 31 over to programmer mode, Control V, and then there it is 0, 0, 0, and then a bunch of 5 ones. Okay, and the number was less than a half, less than a quarter, less than an eighth, but it was only a little bit less than an eighth. So then it was a lot of ones following that. But let's do it if it were 0.123. What if I wanted 16 places? Then I would do times 2 raised to the 16. And I would get 8060. And throw that over into programmer mode, Control V. And then here's my number. So my original 3 zeros, my bunch of 1s, and then zeros and 1s after that. Okay, so that's what I want to show you. I had it in some longer blah, blah, blah in binary numbers, but I just wanted to have it separated short video. And here it is. Thanks for your attention.